This marks the final chapter of the steel hull loading tutorial. In this video, we will demonstrate how to create horizontal wind loads using load transfer surfaces. Before we apply the horizontal loads, we must create the lines to close the open cells, such as the gate of the hull. This step is necessary so that RFEM recognizes them as closed cells and loads them accordingly. You should already have these lines created, but if not, you can easily go up to the new line tool, snap to the column bases of the gable columns, one after the other. Then you just need to repeat this process for the remaining perimeter of the structure. A new and very helpful function in RFEM 6 is the load transfer surface. For the side walls, we can use the rectangular surface. In addition to the load wizards, you can use load transfer surfaces to easily generate loads in RFEM 6. We create this new rectangular surface using the load transfer stiffness type. This is unique and has no structural effect and can be used to consider loads from surfaces that haven't been mounted. In the Load Transfer tab, this is where we can select both directions for load transfer direction, and then we can click OK. For the rectangular surface, all we need to do is click and confirm 2 points. To insert the surface on the front of the structure, we want to use the Select Boundary Surface tool. Again, we choose Load Transfer in both directions. To insert this new surface, we select the boundary lines of the respective surface. If the boundary line consists of several members, we select them one by one. Once all boundary lines of a surface have been selected, the surface is created. Then we repeat this process for all lateral surfaces of the steel hull. We can also use the wireframe view to select the lines more easily. Once we've inserted 2 of the lateral surfaces, we can save time by holding down the Control key to drag and drop them to the other side. We have inserted all of the load distribution surfaces, and now by right-clicking on a surface we can display the local coordinate systems and customize the properties of the load distribution surfaces. Now let's set the wind load in the X direction by clicking on the New Surface Load button. In the new dialog box, we select the correct load case from the list and enter the load properties. Then we click OK to apply the load to the surfaces. We repeat this process for the Y direction as well. We can also customize these loads after the fact. For the suction side, we want to decrease them. In our example, we've entered the wind loads for the roof and the sides of the steel hull in separate load cases. These loads act together from the same directions. We've also assumed that we cannot automatically generate these wind loads on the vertical walls using the load wizard. To consider this interaction, we select the lateral wind loads in the navigator and add them by right-clicking on the respective automatically generated wind loads of the roof. Just for example purposes, I will only be adding the wind load to one of the automatically generated wind load cases. So far, this is how you would manually add the lateral loading for wind loads to the side walls and vertical walls. But I would also like to show you how you can use the wind load wizard tool to automatically generate the loading for the vertical walls. I'm going to go to load case 23, our minimum wind load in the X direction, and delete the loads that we have added manually. Then I will do the same thing for load case 24. Now to have the wind loads automatically generated using the wind load wizard tool for the vertical walls, we can go back under load wizards and then under wind loads into our automatically generated wind load wizard. Under the submenu type, instead of choosing do a pitch roof, we can choose vertical walls with do a pitch roof. As you can see, now we must enter the base corner node numbers, I, J, K, and L. We need to make sure that I, J, K, and L match up with the same order of operations that we have chosen the nodes for A, B, C, D, E, and F. We can choose these graphically using this button right here. I will start off on the same corner that I've chosen A in the previous video. Now, as you can see, we have our set loaded walls down here in the table below. Under load cases again, we want to uncheck our manually created lateral loading. Check them back on, and then have the load wizard generate these load cases automatically. Now we can click OK. And now the loading on our walls is automatically generated for our wind loads. We do have extra minimum wind load cases now, so we can now just easily delete load case 23 and 24, holding Control, selecting both of them, and hitting the delete key on our keyboard. For member structures, ensuring structural stability is crucial. Stiffening bracings can receive compressive forces, and if these are tension members, they fail automatically when absorbing compression forces. We can go to our Display tab, and under Colors of Rendered Objects By, we can go under Members and choose Member Type. In the color panel on the right, you can see tension members are purple, and you can see that our cross bracing is set to tension only. These members will fail automatically when absorbing compressive forces. To avoid this instability, you can activate the Exceptional Handling option in the Reactivation tab of the Static Analysis settings. Alternatively, you can assign a very low stiffness to the failing members or apply pre-stress to the tension members. This pre-stress ensures that tensile forces act constantly on the stiffening members, preventing failure due to compression forces. First, we need to create a new load case. This load case will be a self-straining force. With the self-straining force load case, we can insert a load on the tension members using an axial displacement. We can also give this load case a name of pre-stress. We can select all bracings quickly using the visibilities. Under the Views tab, we can activate visibilities, turn on members, and sort by members by type via tension. Now we can easily select all of our tension members and add in an axial displacement. We'll click on Member Load, change our load type from force to axial displacement, and then we'll enter a small magnitude of 0.5 inches. With these measures in place, we've ensured that no instabilities will occur during the calculation. This concludes the final chapter of the loading of our structural analysis model. Now you have a comprehensive overview of the load cases, actions, combinations, and loads in RFEM 6. In the next video, we will begin the calculation. Until then, thank you for watching.